Hi, hello. I'll be doing something slightly different, and I'll be doing graph sketch question. Quite a peculiar one. I spent quite a lot of time doing this question, and I believe I have a good solution for it, or at least a good method to do this. If good is not the correct word, then a satisfactory one is satisfactory is a better word. So the graph is y equals to sine x to the power of tan x. The first thing to note is the domain. So x can be all real numbers except for um, any number that is any x value that is a multiple of pi by 2. The reason for this is that we know if I sketch the graph of tan, that tan has an asymptote at pi by 2 and multiples of pi by 2. So this is pi and this is 2 pi. So it has a period. Actually, this is the wrong way to write this. Pi by 2 plus pi k, where k is an integer. So this is the correct way to draw it. Um, at these points, tan explodes to infinity. So I will have to see what happens, explore what happens between those values. Now, to check some trivial points like x equal to 0, if we do that, we get 0 to the 0, which is just 1. So we know our graph will start at 1. Um, so I'm gonna draw it on the side here. These are my axes, x, y. This is going to be the point 1, my origin. Now I need to try and see what my behavior between 0 and pi by 2 is. Now, before doing that, I also need to realize that what the tan being the exponent means is that um, tan x between certain values is less than 1. So, for instance, tan x can be a half. That implies that sine x cannot be a negative number. So, uh, to illustrate this with the graph of sine, sine is less than 1 between uh, certain points like pi and 2 pi. That means between pi and 2 pi, there will be no graph of um, sine x to the tan x. So this is very important. So I'm going to extend this a bit. 2 pi. And just for the sake of um, space and also argument, I'll just draw the graph between minus pi by 2 and 2 pi. We know this graph is going to be periodic because sine and tan are both periodic functions. Now, next thing to work out is what happens between 1 and pi by 2. So between 0 and pi by 2, tan tends to grow, and the same is basically the same for pi for sine. But the only difference here is that tan grows indefinitely, it tends to infinity. But at pi by 2, the max sine tends to its maximum value, which is 1. It doesn't tend to, it is its maximum value, 1. So, and this is a very important thing to note of. Something else I also considered is the small angle approximation for tan and sine, which is the same. It's just x. Tan x is equal to x for very, very small angles. But we, I quickly realized that might not be a completely relevant insight. So I need to look at what happens between 0 and 1. So I know that at pi by 4, tan reaches 1. And at pi by 4 here, sine is 1 over 2. 1 over root 2 being less than 1. And by the way, that's going to be another point. So 1 over root 2 to the power of 1. So this is when, if you think of y as a function, y is pi by 4. And this is going to be just 1 over root 2, which is less than 1. So we know that pi by 4, which is halfway here, there's going to be a point that is less than 1. Now, this is very important. Now, between 1 and pi by 4, tan is less than 1, and between 0 and pi by 4, sine is also less than 1, but more specifically is less than 1 over root 2. I think what's important here to note is the way tan grows and sine grows. It seems like my exponent is going to be, sorry, um, if you have a number that's less than 1 and you raise it to the power of something else that is less than 1, then you're going to get a number that is more than the initial value in most cases. For instance, if I have a half raised to a half, that's going to be more than a half. But if I have a half raised to the half squared, then I will have something that is less than half. And that's very something I think very important to understand about small values, values less than 1. So what it seems to me is that between here and here, what happens is something like this. And then we need to investigate what happens at pi by 2. Now, because we can't do that directly because of limits, I'm going to use L'Hopital's rule. I am going to rewrite y equal to sine x to a tan x in this form. I'm going to take logs on both sides. And then I am going to rewrite this as a fraction. So ln sine x is equal to cot x. And we want the limit of this as x tends to pi by 2. Now, I am going to use L'Hopital's rule. And by L'Hopital's rule, that I know that this is the same as me doing differentiating numerator and denominator. The derivative of ln sine x should be cot x. The derivative of cot x is minus cosec squared x. Which is, I can rearrange this very quickly. This becomes minus cosec squared sine squared x. Now, I should just sine. The limit of this, as it tends to pi by 2, cos is going to go to 0. So, sorry, cos is going to go to 0, and sine is going to go to 1. Therefore, it's going to be 0. So we have ln y, the limit of x, as it tends to pi by 2, of ln y is equal to 0. That means y is equal to e to the 0, which is 1, which is a very interesting result, because now we can say that at pi by 2, there isn't an asymptote. I lied, but it goes back to 1. So this is kind of the behavior of the graph. Now, what's interesting is that I cannot say that pi by 4 is my minimum point. To do that, I will have to differentiate this and set it equal to 0. But I will move on for now, and I will try and see what happens after pi by 2, between pi by 2 and pi. We already know that between pi and 2 pi, there is nothing. It's not defined. So let's see what happens between pi by 2 and until pi. So if we look at the tan graph, after pi by 2, tan is a very, very, very small, very, very small negative number. Sorry, very, very large negative number. Because of course, negative numbers are very small. But in terms of the actual value, it's going to be a very, very large negative number. And sine is going to be always something less than 1 until 0. So here is where this idea about small numbers, numbers less than 1, comes into play. So let's say if I have um, 0.9 and I raise it to the power of a very large negative number, this is going to be 1 over 0.9 to the 1000, which is this number, which I assume is going to be more than 1. Well, actually, I think it's better to think about in this terms. And I know raising 0.9 to the 1000 is going to be a number less than 0.9, which means that this is going to be very small number. What is a small number? That means it makes the whole thing, the whole fraction, a bigger number. So we know that my graph is going to be big, more than 1, is going to increase. So what's going to happen after this? First of all, I'm going to check what happens at pi. I should have done that before. Sine pi, which is 0, to the tan pi, which is also 0, which means that I have, again, 1. So at pi, my value is going to be 1. So what happens is that my graph seems to increase, and then it goes to pi, which is in this case 1. So there's something must happen between here and here. We know here the trend here is that it increases, so there must be some sort of thing happening. The way I've reasoned what's going to happen there is that I continued and looked at what happens as we reach to the value of pi. So on the tan graph, we see that eventually we get a number that's quite small, And on this sine graph, we see that it's a number that is also quite small. So actually, what happens when you have a small number, in this case less than 1, raised to another number, raised to something less than 1, is that you don't exceed 1. You don't go more than 1. So we do have that threshold. So it seems to increase, and then it goes back to pi. The things that I couldn't quite figure out, at least I didn't do yet, is to actually work out what the minimus and the maximus seem to be. I can try and do that now. I think differentiating this implicitly might be, this form at least, might be the best thing to do. So I might have to do this by parts. Oh no, I'm not integrating. I am differentiating, so there's no by parts. So it's product rule. Sec squared x ln sine x plus cot x tan x. Now this is 1 over y, so dx, dy over dx is equal to y, so I'm going to bring the y into the other side. X times sec squared x ln sine x. Cot x times sine x is just 1. So this is what my derivative is. I'm going to set it equal to 0. Now, I know that sine x tan x is never going to be equal to 0. So I can divide both sides by it. And I get remaining sec squared x ln sine x plus 1 equals to 0. Now, this is ln sine x over cos x, cos squared x, is equal to minus 1. Now, if I think of the graph of ln sine x, well, sine x is, ln has a domain that has to be more than, it can't be negative, can't be 0. So sine x must be between 0 and pi, which is when it's positive, and all of its um, periods. So actually, the better way to write it is this. And pi plus 2 pi k is an integer. That's very important. Now, this means, if I look at the graph of sine, and in conjunction with the graph of ln, I see that this is 1. So here it's going to be 0. Between 0 and pi by 2, I am going to get always values less than 1. So I'm always going to be here. So my graph of ln sine x is always going to be negative, and it's going to look like this. And this is going to be kind of how it looks like. Now, this is very important because I want to make an argument from this. Ln sine x is equal to minus cos squared x. Cos squared x looks like this. Okay, so if I graph sine x, ln sine x in the same graph, perhaps with different colors, we see it has two intersects, one here and one here. So that means pi by 2 seems to be a solution um, to this equation. So let me quickly plug in pi by 2. Learn sine pi by 2, sine pi by 2 is 1, learn 1 is 0, and minus cos squared pi by 2 is just also 0. So this holds. So this is true. Now my other intercept is going to be much early on, and it seems to be, I have drawn this very badly, and I think there isn't, I need some numerical method to actually, numerical way to actually do this. I don't think there is a nice way to do it without a numerical method. And this pretty much seems to be very close to the origin. So I'm gonna go and refine my drawing to look more like something like this. Oops. And this is very bad. And there seems to be some sort of symmetry in the pi by 2 axis. Um, it's a um, it's odd in the sense that I don't know how to explain it. It seems to be a rotational symmetry um, of 180 degrees on the line pi by 2, which means it's odd if you consider it around pi by 2. Is there a way to prove this? Not that I can think of. The only thing that changes is the fact that before pi by 2, tan is a positive number, and after pi by 2 is a negative number. So perhaps that would explain that. So I guess if I were to extend this, my next point would be like this, and so on. And the same thing can be said on this side of the graph. So this is kind of my final sketch of it. And yeah, that's pretty much it. I enjoyed doing this question. It gave me a lot of headache, but and I know I've explained it very poorly. It's I always blame it on the fact that it's quite late to the night that I'm doing this. But yeah, that's kind of the way I did it. But yeah, I hope it was enjoyable, and I hope you can see the fact that this is quite a hard graph to sketch. So, kudos to you if you did it well. Nice.